Okay, so last time we left off with this exercise, what we're going to do is change the correlation of the X matrix, increasing it, and the idea is that hopefully we're going to see that our betas are going to get increasingly unstable as we increase the rho parameter, which is our correlation in the X variables. So let's see what my solution is. So this is just the code to generate the data. This little def, all it does is it takes it runs a bunch of trials, and it simulates under the for the given parameters for the simulation. So this would be the row parameters, n, p, and so on. And I just wrap them all up into this kwargs. If you haven't seen this before in Python, it's pretty handy if you aren't using classes and you want to pass a bunch of arguments to a def, then you can do this. It's preferred just to use classes, but for such a short example, this is just fine. So what we do is for each trial, we are going to simulate, or we're going to run ordinary least squares, which is through the linear regression class in the linear model. We're going to fit it to the current data, the current simulation, and then we're just going to return all of the betas at the end. Okay? And so let's just look at the first coefficient for all of these for each row. So I'm just going to do this in list comprehension. So for every row in rows, I'm going to run this method and then just extract the first beta and then take its variance. This is a little bit condensed. Maybe it's a bit more condensed than we would actually like, but yeah, so this is it. And then if we plot it, we see what we expect, which is that as the X correlation, the row increases, approaches 1, we have that the variance of beta is diverging. Okay, so that just verifies that our ordinary least squares is going to get increasingly unstable as our X columns are getting closer to one another, which happens with high probability if you have high correlations in your X variables. Okay, so before I mentioned that this was equivalent to Gram-Schmidt, and we used that to extract this QR decomposition from successive orthogonalization. I asked you to do this as an exercise. So let's jump back and do this. And it's very simple. Effectively, it's already in the algorithm itself, but all we have to do is just observe that in Gram-Schmidt, the idea is that we successively project each new vector, so this is each new X, onto the previous vectors. And the previous vectors, the hope is that they're orthogonal. Right? So we do this successive projection and then just subtract off the projection from the X to get the new Z, right? So that's the idea, and all we have to do is observe that the projection operator of, say, X onto Z looks like this, right? You just take X inner product with Z, divide it out by the norm of Z squared times Z itself. Right? That's the projection of X onto the space, column space of the space spanned by Z. And so in Gram-Schmidt, this is what we have to calculate, but that actually just turns out to be that gamma hat times Z. Right? And so because we get that this is actually the projection of X onto Xj onto Zk, then this is just subtracting off that projection successively from each of the Xj's. And so this is just doing Gram-Schmidt. Okay. So that was the QR decomposition through successive orthogonalization, right? And then another way to think about the X and what ordinary least squares is doing is through a different decomposition, the singular value decomposition. And this is going to come up in a lot of different cases, including PCA and yeah, it's going to be ubiquitous. So it's very important to get accustomed to the singular value decomposition. The SVD, singular value decomposition, is very simple for this rectangular matrix X. X can be written as U, D, V transpose, where D is diagonal, right? And U and V are orthonormal. And so typically, if n is greater than p, we can write U as an n by p matrix. D is diagonal and V is p by p. That's one way we can write it. So because U is orthonormal, that means that U transpose U is equal to the identity. And in full generality, we would make U be n by n. D would actually be the one that was rectangular. It'd still be diagonal. It would only be non-zero on the ith entries. And V would be p by p. That's in full generality. But when n exceeds p, we can, without loss of generality, make it look like this, where U is the n by p, is the rectangular one. So this just happens for rectangular X. And now, if X is singular, what ends up happening, so that's when X transpose X is non-invertible, there will be some non-zero vector such that X times Z is equal to 0, right? And what that means is that some eigenvalue of X is going to be 0, which means that one of the elements of D, one of the diagonal elements of Z, is actually going to be 0. And that's equivalent to one of the residuals in the successive orthogonalization being 0, right? Because eventually our Z's are going to span the entire column space of X, so the entire p-dimensional space of X. And so eventually we would get that 1 is 0, because otherwise it actually has a smaller dimension. The column space would have a smaller dimension than p. Okay, so that's one way we can think about the singular value decomposition. One nice thing is that both U and V in this decomposition are orthogonal, right? Where before we had an upper triangular matrix, which was still easy to invert, but it's not as easy as the orthonormal matrices, for obvious reasons. So, but the downside is that it's generally more expensive to compute the SVD than the QR decomposition. So for practical purposes, we generally don't work with the SVD. We work with things like Cholesky decomposition or QR decomposition. But for our purposes, just for our understanding purposes, it's really nice to work with the SVD in the theory. So one thing that we can do is look at what Betahat actually is based on the SVD, right? So this is something that I think if you're taking my class that I'm going to assign as a homework to verify this, but it's pretty straightforward. It's just one part of the exercise, and we're going to do something very similar to this with ridge regression in a little bit. Okay, so if we think about U, or if we think about X, that's U, D, V transpose. U is n by p, D is p by p, and V is p by p. D is diagonal. Then the Gram matrix is X transpose X. That's it, or this matrix. Sometimes this is called the Gram matrix. And this is equal to, if we just plug in the singular value decomposition, this is V, D, U transpose times U, D, V transpose. D is, because it's square, D is symmetric. And diagonal, it's symmetric. Now, because of orthonormality of U, this is just equal to the identity, and we just get V times D squared times V transpose. This is called the spectral decomposition. It turns out that this is a regular matrix, so it has a spectral decomposition, right? And its eigenvalues are these D squareds, right? And so what you can do is, using this, the normal equations, is derive that this beta hat is actually equal to VD inverse U transpose Y, right? So let's just make sure the dimensions work out well. This U transpose Y, this is now, U was n by P, so U transpose is P by N, So we have a p by n times an n vector. That's a p vector. Right? So we have a p vector here. D inverse is p by p, and v is p by p as well. So all of this adds up to gives us a p vector, which is beta hat. So the dimensions work out. Great. Okay, so this is our coefficient formula for beta hat. So let's think about this. What does this mean? If we look at beta hat, what this means is we take our uj transpose y, right? So we compute that, and then we take dj inverse and multiply that by vj. And we can sort of compare this to what happened with successive orthogonalization. In that case, we had these gammas that were multiplying our everything. And those gammas had, in the reciprocal, this squared norm of the z, right? And in the reciprocal now, we have the the singular values of x. Right? And so very similarly to what happened there with successive orthogonalization, where we had this instability due to these small residuals when we regressed x onto the other x's, now we have that beta hat is unstable if the eigenvalues, or the singular values, are very small, right? Because when we invert them, they become very big. And if we think about this uj transpose y, this is some noisy entry, right? uj transpose y is something that presumably has some label noise incorporated into it. And so if that label noise is large, it has some variance. And then if you multiply it by an extremely large number, the variance gets multiplied. And so that's what would cause the instability of our beta hat, are these small eigenvalues. So that's another way to think about instability in beta hat with respect to the x, the design matrix. Okay, so now let's do an exercise that gets at this same thing, but now with respect to the SVD. So I'm going to give you some code for computing the SVD of x transpose x. Now we're going to take the same selection of rows as before. So just go back, take the same list. For each row, take that same x simulation and compute our singular values, and then plot them. So for a given generation for a given x, we can take our singular values and we can plot them in order from largest to smallest. And then let's just change row and then get another simulation of x, get another set of SVDs, and then plot the singular values from largest to smallest. And in this case, the singular values of x transpose x are just the eigenvalues. So we're going to plot the eigenvalues from largest to smallest. And now the question is, what does this say about the stability of beta hat as rho approaches 1? Right? So let's look at the simulation code really quickly. This NP, let's just set these to be 100, 8, and 0.8 for row. And we're going to change row, but let's just start with it being 0.8. Let's compute our betas as before and set our sigma equal to 1. Then we could generate x and y just like before. But now let's do the SVD of x. Let's look at D for this SVD of x. So D is the the singular values of x. So we could have instead used the eigen decomposition, the spectral decomposition of x transpose x. That would have also worked. We would have gotten the squared singular values. But let's just look at the singular values themselves. Okay. So let's just double check a couple of things. Let's double check that that U, V, and D are the right shape. So it's 100 by 100, 8 by 8, and 8 by nothing for D. Okay, so that makes sense. U is n by n in this case, right? But we're only going to be interested in D anyway. And now let's just double check that if we take our U interproducted with a diagonal D and then V, that we're going to end up getting, we're going to reconstruct X. And this U up to P, this is the n by P matrix. So this is just double checking to make sure that that we actually do have the SVD and that we understand the shape of these eigenvectors. So if we look at the x, take its absolute value of these difference, and then sum them up, we get something very small. So this is actually the SVD. Okay, so go back and calculate this for all rows in our list, and then for each one, just plot the D's from largest to smallest.